Please subscribe to support the channel. Most stars that we gaze at in the night sky, from the blazing sun overhead to the distant twinkling points of light scattered across the Milky Way, share something fundamental in common. They are made of atoms. Hydrogen and helium, the simplest atoms in the universe, dominate their makeup, and the furious nuclear reactions in their cores give rise to the light and warmth that sustain planets like our own. But here's the captivating twist. Not every star in the universe may be bound by this familiar atomic recipe. Somewhere out there, perhaps lurking unseen, there could exist stars that aren't made of atoms at all. These would be stars so alien to our understanding that they challenge the very foundation of what we call stellar. They would not burn, not shine, and not rely on the same physics that powers the sun. Instead, they would represent a completely different form of matter and energy bound together under the crushing influence of gravity. Just the thought of a star existing without atoms rewrites the assumptions we've held for centuries about how the cosmos is built. This is where our journey begins, with the provocative idea that the universe may harbor a class of stars fundamentally different from anything we've ever directly observed. These strange objects that break away from everything we normally associate with stars are known as boson stars. The very name hints at their uniqueness, because they are thought to be built not from the usual matter, protons, neutrons, and electrons, but instead from a completely different category of particles, bosons. To appreciate how unusual that is, let's pause for a moment and recall what stars normally are. Every star we see shining in the sky is essentially a vast ball of plasma. Atoms of hydrogen and helium are torn apart into nuclei and electrons by intense heat, and under the immense pressure of gravity, those atomic nuclei fuse together. That fusion produces light and heat, which then streams outward across space. This is the familiar story of stellar physics, the one astronomers have used to explain everything from the twinkle of distant suns to the fiery life cycles of massive stars. But boson stars? They don't follow that script at all. These hypothetical objects are not built on the framework of atoms. They don't need the proton-neutron-electron trinity that makes up regular matter. Instead, they are theorized to be composed of a vast, collective state of bosonic particles. Imagine a star that is not a giant ball of atomic plasma, but a kind of cosmic condensate of exotic particles, all overlapping in strange harmony. It's like stepping into a parallel version of astrophysics, where the rules are deeply rooted not in chemistry or nuclear fusion, but in the abstract mathematics of quantum fields and relativity. The term boson star comes from the idea that such stars could form if the universe contains certain kinds of bosons, ultralight, fundamental particles that don't behave like the matter we are made of. These bosons could condense under gravity into a stable, self-gravitating object that, at least on the outside, resembles what we might call a star. The big difference is that it would not shine, it would not fuse, and it would not be built from any atom in the periodic table. This is why boson stars often capture the imagination of physicists and cosmologists. They stretch our concept of what a star can even be. It's important to emphasize that boson stars are not something we've seen directly. No telescope has photographed one, no probe has flown past one. They exist right now only as solutions to equations and as predictions of certain models of physics. But the fact that they arise naturally from the marriage of Einstein's general relativity with quantum field theory makes them compelling. In physics, when two great frameworks point toward a new kind of object, it's worth paying attention. Boson stars may be exactly such an object. What makes this idea even more tantalizing is that it does not require physics that is wildly speculative or alien. Instead, it relies on extending principles we already know. We already know bosons exist. Photons, gluons, and the Higgs boson are just some examples. We also know that bosons behave very differently from the fermions that make up regular matter. So the question becomes, if the universe contains certain kinds of undiscovered bosons, could gravity assemble them into large, stable objects? Theoretical work strongly suggests the answer is yes, and those objects are what we call boson stars. To fully appreciate how revolutionary this idea is, think of it this way. For centuries, we've understood stars as atomic engines. Even the wildest, most exotic stellar remnants we know, white dwarfs, neutron stars, black holes, are still linked, in one way or another, to the atomic matter that once made up a star. Boson stars break that link. They represent a path where matter organizes on a cosmic scale without atoms ever being involved. It's a bit like imagining life without cells, a completely alien construction that still fulfills the role, but in a way we wouldn't have expected. Boson stars are, in essence, stars that are made not of matter as we know it, but of fields. They are the kind of objects that force us to broaden our vocabulary. When we say star, we don't just mean ball of burning gas. We may need to mean any self-gravitating, long-lived configuration of particles or fields. That's the profound conceptual leap boson stars invite us to take. When we talk about normal stars, like our Sun, we are talking about immense nuclear furnaces that draw their energy from one of the most fundamental processes in the universe, nuclear fusion. At the heart of a typical star, temperatures soar to millions of degrees and pressures reach unimaginable levels. Under these extreme conditions, hydrogen atoms, the simplest and most abundant element in the cosmos, are forced so close together that their positively charged nuclei overcome their natural repulsion and fuse. This fusion process transforms hydrogen into helium, releasing staggering amounts of energy in the process. That energy radiates outward from the core in the form of photons, which bounce around inside the star for thousands or even millions of years before finally escaping into space as the visible light we see. It also manifests as heat, keeping the star in equilibrium against the crushing inward pull of gravity. This balance between gravity pulling inward and fusion pushing outward is what allows stars to shine steadily for billions of years. Without fusion, a star like the Sun could never exist as we know it. It would simply collapse under its own weight or disperse into space. The key point is that ordinary stars are atomic in nature. They are powered by the fundamental interactions between protons, neutrons, and electrons. Every stage of a star's life cycle, from its fiery birth in a collapsing cloud of gas, to its long main sequence lifetime, to its spectacular death as a supernova or a quiet fade into a white dwarf, depends on atoms being present. Hydrogen atoms provide the fuel, helium and heavier elements provide the ash, and nuclear fusion serves as the beating heart of the process. For example, our Sun has been steadily fusing hydrogen into helium for about 4.6 billion years and will continue to do so for several billion more. More massive stars burn through their fuel faster, fusing heavier elements as they age, while smaller stars can burn dimly but stably for trillions of years. In every case, though, the pattern is the same. Atoms are the fuel, fusion is the engine, and light is the output. This is what makes the concept of boson stars so startling. They don't follow this atomic recipe at all. There's no hydrogen to fuse, no helium ash, no chain of fusion reactions creating light and heat. Boson stars, if they exist, must be powered, or rather, stabilized, by entirely different physics. They represent an entirely new kind of stellar existence, one that doesn't rely on nuclear fusion to shine. What if a star didn't need atoms at all to exist? That single question cuts straight to the heart of the mystery surrounding boson stars and captures why physicists and astronomers are so intrigued by them. It takes everything we think we know about the cosmos, everything rooted in atoms, chemistry, and nuclear physics, and flips it on its head. For centuries, humanity has lived with the assumption that stars, planets, and people all share the same basic ingredients: protons, neutrons, and electrons, bound together into atoms. But what happens when we ask whether stars can exist without any of those ingredients? It's a daring question because atoms are so fundamental to the way we experience reality. Atoms build the air we breathe, the light bulbs that glow, the very cells in our bodies. And on cosmic scales, atoms fill galaxies with the gas and dust that form new stars and planets. Stars themselves, the shining beacons of the night sky, are gigantic laboratories of atomic interaction. Hydrogen atoms fuse, creating helium and heavier elements, seeding the universe with the stuff of life. Without atoms, we wouldn't be here to ask the question in the first place. So how could there be stars without them? The key lies in shifting our perspective. What defines a star? Traditionally, we call something a star if it is a self-gravitating sphere of matter that produces energy, typically through nuclear fusion. But is fusion the only way nature can stabilize such an object? Is it possible that gravity could bind together not atoms, but some other form of matter entirely? That's where the central question leads us. Maybe stars don't need atoms. Maybe there's a different path to creating stable, massive objects that don't shine in the traditional way but still deserve the title of star. This isn't just idle speculation. The very equations of physics themselves allow us to ask this question. Einstein's general relativity tells us how gravity shapes space-time, bending and warping it in the presence of mass and energy. Quantum field theory tells us how particles behave on the smallest scales, including not only familiar fermions like electrons and protons, but also bosons, which obey entirely different rules. When scientists combine these two pillars of modern physics, surprising possibilities emerge. Among them are solutions that describe objects which are not made of atoms at all, but of bosonic fields that gather under gravity to form star-like bodies. By asking whether a star can exist without atoms, we are pushing into the very frontier of our understanding. It's similar to when early astronomers first realized that not all celestial objects were stars. Some were planets, others were comets, and some distant nebulae turned out to be galaxies of their own. Each time we expand our definition of what the universe contains, we discover it to be richer, stranger, and more profound than we thought. Boson stars represent that same kind of expansion. They ask us to consider that star doesn't have to mean ball of atomic fusion. Instead, it could mean any stable, massive structure held together by gravity and governed by quantum laws. Imagine the implications if the answer to this question is yes, if stars without atoms not only can exist, but do exist, perhaps in great numbers. That would mean that the universe harbors entire populations of invisible stars, lurking in the dark, unseen by traditional telescopes because they emit no light. It would mean that the cosmos has been hiding a whole new category of astrophysical object, waiting for us to notice its gravitational footprint. It would mean that the story of stellar evolution, which we thought we had mapped out from main sequence stars to white dwarfs, neutron stars, and black holes, is not complete. There's another branch to the family tree, one that doesn't depend on atoms at all. The central question also connects directly to the greatest mysteries in physics today: dark matter and dark energy. For decades, astronomers have known that most of the universe is invisible. Galaxies rotate too quickly, clusters of galaxies bend light too strongly, and the large-scale structure of the cosmos cannot be explained by visible matter alone. Something unseen, something not made of atoms, is exerting its gravitational influence everywhere we look. Could boson stars be part of that hidden component of the universe? If stars can exist without atoms, perhaps they are not rare oddities, but widespread players in the cosmic drama, shaping galaxies and influencing cosmic evolution in profound ways. By asking this question, what if stars didn't need atoms at all? Scientists are not only imagining a new kind of star, they are also probing the very foundation of matter, energy, and gravity. They are exploring the deep intersection between the quantum world, where particles obey strange rules of overlap and probability, and the cosmic stage, where gravity sculpts the universe on the largest scales. A boson star is more than just a hypothetical astrophysical object. It is a meeting point between the two most powerful theories in science, and a potential clue to unlocking the nature of the unseen universe. And perhaps most importantly, this question reminds us that science is about challenging assumptions. The sun shines because it burns atoms. That's true. But does that mean every star in the cosmos must shine the same way? History warns us against such certainty. We once believed Earth was the center of the universe. We once believed the stars were unchanging points of light. We once believed the Milky Way was all there was. Every time, reality turned out to be bigger, stranger, and more fascinating. So when we ask if a star can exist without atoms, we are continuing that tradition of curiosity, a willingness to imagine that the universe might be stranger than we ever dreamed. To understand why boson stars are so radically different from the stars we know, we first need to step back and talk about the basic building blocks of matter and energy. In physics, every particle in the universe falls into one of two great categories: fermions or bosons. These categories aren't arbitrary labels. They represent two fundamentally different kinds of behavior in the quantum world. The distinction between them lies at the very heart of why normal stars are made the way they are, and why boson stars, if they exist, must be made of something entirely different. Let's start with fermions. Fermions include particles like electrons, protons, and neutrons, the essential components of atoms. The defining feature of fermions is that they obey something called the Pauli exclusion principle, a rule discovered by Wolfgang Pauli in 1925. This principle states that no two fermions can occupy the exact same quantum state at the same time. In simpler terms, fermions don't like to be crowded. They insist on individuality, always keeping at least a little separation in terms of their quantum properties like position, spin, or energy level. This is why atoms have well-defined structures. Electrons occupy specific shells around the nucleus, each orbiting in its own distinct quantum state. Without the exclusion principle, the orderly architecture of matter would collapse. Because fermions resist crowding, they create what physicists call degeneracy pressure. Imagine a box filled with electrons. If you try to compress them, their quantum nature pushes back, not because of physical forces in the usual sense, but because the exclusion principle simply won't allow them all to sit in the same state. This pressure becomes incredibly important in astrophysics. It's what prevents white dwarfs from collapsing under gravity. The electrons resist being squeezed further. It's also what holds up neutron stars, where the neutrons themselves provide the degeneracy pressure. In short, fermions are the reason why normal stars and stellar remnants are structured the way they are. Now let's look at the other side of the coin, bosons. Bosons include particles like photons, which are particles of light, gluons, which hold atomic nuclei together, W and Z bosons, which govern the weak force, and the famous Higgs boson, discovered in 2012. Unlike fermions, bosons do not obey the Pauli exclusion principle. Instead, they follow a very different set of quantum rules. Multiple bosons can occupy the exact same quantum state at the same time, stacking on top of one another without resistance. This leads to remarkable phenomena in nature. For example, the laser is possible because photons, which are bosons, can all occupy the same state, traveling in perfect synchrony. Similarly, in certain ultra-cold conditions, atoms made of bosons can collapse into a single quantum state, forming what's called a Bose-Einstein condensate. In such a condensate, millions or billions of particles act as though they are one giant particle, all overlapping and behaving in unison. This ability to pile together without exclusion makes bosons incredibly different from fermions, and it's exactly this property that makes boson stars theoretically possible. Think of it this way: fermions are like people at a theater, where each person insists on sitting in their own seat. Bosons, on the other hand, are like beams of light. Countless photons can stream through the same space, overlapping without objection. Fermions create matter as we know it, with its solidity, structure, and resistance to compression. Bosons create forces, fields, and collective states where individuality dissolves into harmony. When we bring this distinction back to stars, the contrast is striking. Normal stars are made of fermionic matter, protons and neutrons in their cores, electrons orbiting around nuclei, all subject to the exclusion principle. The very existence of atomic structure and nuclear reactions depends on fermionic behavior. Boson stars, however, would be built from bosons, particles that are perfectly willing to crowd into the same state, overlapping in ways fermions never could. Gravity would pull these bosons inward, but instead of collapsing into a singularity, their collective quantum nature could stabilize them into a new kind of star. This difference, fermions versus bosons, is not just a technicality. It's the dividing line between the familiar world of matter and the exotic world of fields. It explains why you and I, and the Earth beneath our feet, are made of fermions, while light, forces, and possibly even whole stars could be built from bosons. By understanding this fundamental dichotomy, we begin to see why boson stars don't just sound unusual, they are unusual at the most basic level of physics. Bosons are extraordinary precisely because they break free from one of the strictest rules in the quantum world, the Pauli exclusion principle. Unlike fermions, which jealously guard their individuality, bosons happily share. They can occupy the same place, in the same state, at the same time. This single fact changes everything about how they behave and, ultimately, why they can form the basis of exotic objects like boson stars. To appreciate this, let's first revisit the Pauli exclusion principle. Fermions, such as electrons, neutrons, and protons, cannot exist in the same quantum state as another fermion. If one electron occupies a particular energy level in an atom, another electron is forbidden from sitting in exactly the same configuration. This rule is what gives rise to the beautifully layered shells of atoms, which in turn create the complexity of chemistry and the structure of matter. Without the exclusion principle, every electron in the universe might collapse into the lowest energy state, leaving no diversity, no atoms, no molecules, no solid matter. Bosons, however, are not bound by this law. For them, there is no such prohibition. If one boson is in a given state, other bosons are not only allowed to join it, they are statistically more likely to do so. This phenomenon is called Bose enhancement. It means that bosons naturally clump together in the same state, amplifying each other rather than excluding one another. Instead of resisting crowding, bosons embrace it. One of the most dramatic demonstrations of this comes from light itself. Photons, which are bosons, can all occupy the same quantum state, moving in perfect harmony. This is why lasers exist. A laser beam is a stream of photons, all traveling together in the same direction, with the same energy, in phase with one another. Imagine trying to do that with fermions. It would be impossible. Electrons or protons would refuse to overlap in the same way. Another striking example is the Bose-Einstein condensate, BEC, first predicted by Albert Einstein and Sachendranath Bose in the 1920s and finally created in the laboratory in the 1990s. When certain types of atoms that behave like bosons are cooled to temperatures near absolute zero, they suddenly collapse into a single, unified quantum state. Instead of behaving like a collection of individual particles, they act as though they are one giant superparticle. Millions of atoms move in lockstep, indistinguishable from one another, their wave functions overlapping perfectly. This is bosonic behavior at its most dramatic. Individuality dissolves, and collective harmony emerges. Now, extend this property to the scale of stars. If you imagine a vast number of bosons under the influence of gravity, they don't resist one another the way fermions do. They can sink into the same state, overlapping again and again, forming an object where the usual pressures that stabilize stars, like electron degeneracy in white dwarfs or neutron degeneracy in neutron stars, aren't needed. Instead, the boson's ability to pile into the same state allows a new form of equilibrium. Quantum mechanics steps in to provide stability in a way fundamentally different from what we see in fermionic matter. This is the foundation of the boson star concept. The fact that bosons don't obey the exclusion principle means they can clump together under gravity without the fierce resistance that fermions provide. That clumping could produce a dense, compact object that looks star-like in mass and structure but is utterly alien in composition. Rather than being powered by fusion, its existence would be sustained by the strange quantum harmony of bosons overlapping in the same state. In some ways, boson stars could be thought of as cosmic-scale Bose-Einstein condensates, except instead of forming in ultra-cold laboratories, they would form in the universe itself, shaped and compressed by gravity. They wouldn't shine like the sun, but their presence would still leave detectable marks on the cosmos through gravity. What makes this so compelling is that bosons already play a huge role in the universe. Photons are bosons, and without them, we wouldn't see light. Gluons are bosons, and without them, atomic nuclei would fall apart. The Higgs boson gives particles their mass. Bosons are not an exotic sideshow, they are woven into the very fabric of reality. The idea that other, as yet undiscovered bosons could gather together to form massive, stable objects is not as outlandish as it might first sound. It is a natural extension of their most defining characteristic, the ability to overlap freely, piling into the same quantum state again and again. So, when we talk about boson stars, we are really taking one of the strangest and most beautiful rules of quantum mechanics, the fact that bosons can all exist together in perfect overlap, and imagining what happens when that principle plays out on a cosmic scale. The result is a star that doesn't need atoms, doesn't need fusion, and doesn't shine in visible light, yet could still exist as a stable, gravitationally bound object in the universe. To understand how boson stars could form, we have to dive into one of the more abstract yet powerful concepts in modern physics: scalar fields. At first glance, the term might sound intimidating, but scalar fields are simply fields that assign a single value, a number, to every point in space and time. Unlike vector fields, which have both magnitude and direction, think of wind speed and direction, scalar fields just have magnitude. Temperature, for instance, is a familiar example of a scalar field. At every point in a room, you can assign a number that tells you the temperature at that spot. Now, In the realm of quantum physics, scalar fields can be associated with fundamental particles. The most famous example is the Higgs field, a scalar field permeating the universe, responsible for giving mass to fundamental particles through their interaction with it. The discovery of the Higgs boson in 2012 was monumental because it provided experimental confirmation that such a scalar field truly exists. This proof gives credibility to the idea that there might be other, undiscovered scalar fields lurking in nature. Boson stars, according to theory, could be made of bosons associated with such exotic scalar fields. In particular, physicists are intrigued by the possibility of ultralight particles, far lighter than anything we've detected so far. These ultralight bosons, if they exist, could have masses so small that their quantum wave-like behavior becomes significant on astrophysical scales. Instead of behaving like point-like particles, they would behave more like waves stretched across kilometers or even entire galaxies. Here's where it gets fascinating. If a vast collection of these ultralight bosons clumps together under the pull of gravity, their wave-like nature could prevent them from collapsing completely, creating a stable, self-gravitating structure, a boson star. This is fundamentally different from how fermionic stars, like white dwarfs or neutron stars, stabilize themselves. Instead of degeneracy pressure, the stability of a boson star would emerge from the interplay between gravity and the quantum field properties of these ultralight bosons. Think of it like this: a neutron star is supported by the quantum rule that neutrons, as fermions, refuse to share the same state. A boson star, on the other hand, is supported by the quantum rule that bosons are perfectly happy to share, and in sharing, they create a coherent field configuration that resists collapse. It's almost as though the bosons, overlapping in unison, form a giant standing wave of matter, balanced delicately by gravity. These scalar fields that give rise to boson stars are not just mathematical inventions. They also provide a tantalizing link to some of the greatest puzzles in cosmology. Many theoretical models propose that dark matter, the mysterious substance that outweighs ordinary matter by a factor of 5 yet remains invisible, could be made of scalar fields composed of ultralight bosons. If that's true, boson stars could be the astrophysical expression of this otherwise hidden component of the universe. Another reason scalar fields are so important in the boson star story is that they naturally arise when physicists extend Einstein's theory of general relativity. When scalar fields are added to the equations that describe spacetime, new solutions appear, and among those solutions are stable, compact objects, boson stars. In other words, the mathematics itself tells us that if scalar fields exist in nature, boson stars should be possible. To ground this in a more intuitive image, imagine spacetime as a stage. Fermionic matter, like atoms and stars, are the actors moving across it. Scalar fields, on the other hand, are like invisible lighting that suffuses the stage itself. We don't always see it directly, but its presence shapes everything. If certain exotic scalar fields exist, they may gather into coherent, star-sized clumps, manifesting as boson stars. What makes this especially exciting is that scalar fields are not just theoretical curiosities. They are actively being searched for in laboratories and in astrophysical observations. Experiments designed to hunt for ultralight particles, like actions or action-like particles, are underway. These particles are prime candidates for forming scalar fields and, by extension, boson stars. If scientists detect them, it won't just be the discovery of a new particle. It will also open the door to a whole new class of astrophysical objects. So, the introduction of scalar fields into the story of boson stars is more than just a technical detail. It is the bridge between the tiny, quantum world of fundamental particles and the vast, cosmic world of galaxies and stars. Boson stars are what you get when scalar fields, gravity, and quantum mechanics meet in a cosmic dance, creating objects that defy our usual understanding of what a star is supposed to be. The mention of scalar fields and ultralight bosons naturally leads us into one of the greatest unsolved mysteries of modern science: dark matter. For decades, astronomers have known that the stars, gas, dust, and planets we can see make up only a tiny fraction of the universe's mass. Galaxies rotate too quickly for their visible matter alone to hold them together. Clusters of galaxies bend light from background sources far more strongly than ordinary matter can account for. The large-scale structure of the cosmos, the cosmic web of galaxies stretching across billions of light-years, simply cannot exist in its current form without an enormous amount of invisible mass. That invisible component is what we call dark matter, and by the best estimates, it makes up about 85% of the matter in the universe. But what is it? Despite decades of searching, we still don't know. And this is where bosons and boson stars enter the picture. Some scientists strongly suspect that dark matter may be made not of exotic, heavy particles like the once popular WIMPs, weakly interacting massive particles, but instead of extremely light bosons, such as actions or action-like particles. These ultralight bosons would be almost ghostly in nature, barely interacting with normal matter or light, but still carrying mass and responding to gravity. Here's where the connection deepens. If the universe is filled with ultralight bosons as a form of dark matter, then under the right conditions, those particles could gather together and form boson stars. In other words, boson stars might not just be hypothetical oddities of theoretical physics, they might be an integral piece of the cosmic puzzle, actual astrophysical manifestations of dark matter. This possibility is thrilling because it provides a direct observational pathway to understanding dark matter. If boson stars exist and we can detect them, they would serve as natural laboratories for studying the properties of dark matter particles. Their masses, sizes, and distributions would give us critical clues about what kind of particles make up the unseen bulk of the universe. For example, consider ultralight bosons with masses a trillion times smaller than the electron. Such particles would have enormous de Broglie wavelengths, meaning their wave-like properties would stretch across macroscopic or even galactic scales. This wave-like nature could prevent dark matter from clumping on very small scales, solving long-standing problems in cosmology, such as why dwarf galaxies contain fewer small-scale structures than traditional dark matter theories predict. In this scenario, boson stars could form naturally as dense regions of this wave-like dark matter. Some researchers even suggest that boson stars could make up part of the dark halos surrounding galaxies. These halos are the invisible cocoons of dark matter that cradle every galaxy, including our own Milky Way. If boson stars are sprinkled throughout these halos, they would represent compact, star-sized pockets of dark matter, invisible to our eyes but detectable through their gravitational effects. The connection between boson stars and dark matter also redefines how we might search for them. Traditional telescopes won't help much, since boson stars don't shine. Instead, we would look for them through their gravitational influence, how they bend light from distant stars, how they tug on nearby gas and stars, or how they merge to create gravitational wave signals. Every one of these potential signatures is already being probed by modern instruments like the Hubble Space Telescope, the James Webb Space Telescope, and gravitational wave observatories such as LIGO and Virgo. If evidence of boson stars ever emerges, it won't just be the discovery of a new kind of astrophysical object. It will likely be the long-sought answer to the dark matter mystery. Imagine that, two of the biggest puzzles in physics, the existence of boson stars and the nature of dark matter, may actually be one and the same. That's why so many scientists are excited by this connection. It isn't just theoretical speculation, it's a roadmap that could lead us to one of the most profound discoveries in the history of science. One of the most fascinating aspects of boson stars is the way they achieve gravitational balance. In every kind of star or stellar remnant, the central struggle is always the same. Gravity pulls matter inward, threatening to collapse everything into a singularity, while some opposing force pushes outward, resisting that collapse. For ordinary stars like the Sun, the outward push comes from the immense pressure generated by nuclear fusion. For white dwarfs, it's the electron degeneracy pressure that holds gravity at bay. For neutron stars, the neutrons themselves provide the degeneracy pressure. But boson stars take a completely different path to equilibrium, one that relies on the strange quantum nature of bosons themselves. Imagine gravity as an ever-tightening grip. Left unchecked, it drags all matter inward, crushing it into an ever smaller volume. For normal matter, there's only so much compression fermions can endure before degeneracy pressure slams down the brakes. But bosons don't resist in the same way. They don't follow the Pauli exclusion principle that makes fermions push back. So how can bosons, which love to pile into the same state, resist gravity's relentless pull? The answer lies in wave mechanics. Bosons, especially ultralight bosons, behave as both particles and waves. When a huge number of them gather under gravity, their overlapping wave functions form a coherent quantum state. This state resists compression not because the particles are unwilling to share space, but because their wave-like nature generates a kind of quantum pressure. If you try to squeeze a boson star smaller, the wave functions of the particles spread out in such a way that they push back against further collapse. This is sometimes called quantum pressure or gradient pressure, and it's fundamentally different from the degeneracy pressure of fermions. It's as though the bosons, while willing to overlap, create a standing wave pattern, a delicate quantum structure that simply doesn't allow itself to shrink past a certain point. The inward tug of gravity is balanced by the outward swell of the bosonic field. The result is a stable configuration, a boson star. This balance is elegant because it's born from the very principles of quantum mechanics. Gravity, described by Einstein's general relativity, warps spacetime and pulls mass inward. Quantum mechanics, governing the behavior of bosons, spreads their wave-like existence outward. The star exists in the tension between these two regimes, at the very intersection of relativity and quantum theory. That's why physicists are so fascinated by boson stars. They're not just astrophysical oddities, but natural laboratories for testing the harmony between the two great frameworks of modern physics. Let's compare this more concretely. In a neutron star, gravity is so intense that it crushes protons and electrons into neutrons. The neutrons, being fermions, refuse to occupy the same state, creating neutron degeneracy pressure that halts the collapse. But in a boson star, there is no such degeneracy pressure. Instead, the collective wave nature of bosons produces an oscillating field configuration. This oscillation effectively creates an outward force, preventing gravity from winning the battle. The bosons don't resist crowding. Rather, their overlapping waveforms generate the resistance in a far more subtle, wave-based manner. The exact size and mass of a boson star depend heavily on the properties of the bosons themselves. If the bosons are extremely light, their wave-like behavior dominates, and the star can spread out over enormous distances. If the bosons are heavier, the star can be much more compact. In either case, the fundamental principle remains. Gravity pulls inward, and the quantum field properties of bosons push outward, reaching a stable balance. This idea also reveals why boson stars are so mysterious. Unlike ordinary stars, which shine brightly as fusion releases energy, boson stars don't emit light. Their stability comes entirely from this invisible balance between gravity and quantum fields. They don't blaze in the sky. Instead, they lurk unseen, detectable only through the gravitational influence they exert on their surroundings. Ultimately, the equilibrium of a boson star embodies one of the most profound themes in science. That order can emerge from the interplay of opposing forces. Just as planets orbit in balance between inertia and gravity, just as atoms exist in balance between attraction and repulsion, boson stars exist in the balance between the crushing weight of gravity and the subtle resilience of quantum waves. It's a dance between the largest forces in the cosmos and the tiniest rules of quantum mechanics, played out on a stellar scale. To really grasp the strangeness of boson stars, it helps to set them side by side with one of the most extreme and well-studied stellar remnants we know, the neutron star. Neutron stars are themselves astonishing objects, born from the fiery deaths of massive stars in supernova explosions. When the core of such a star collapses, gravity overwhelms the ability of normal atomic structure to resist. Electrons and protons are crushed together to form neutrons, leaving behind a sphere no larger than a city but containing more mass than the Sun. The result is one of the densest forms of matter in the universe, second only to black holes. The reason neutron stars don't collapse completely into black holes is thanks to the Pauli exclusion principle. Neutrons are fermions, and like all fermions, they refuse to occupy the same quantum state. This refusal generates neutron degeneracy pressure, an invisible but immensely powerful form of resistance. Even though gravity is trying to crush the star further, the neutrons simply won't let themselves be squeezed into the same state. It's this quantum mechanical stubbornness that holds a neutron star up against collapse. Boson stars, however, play by a very different set of rules. Bosons don't care about individuality. They're perfectly willing to pile into the same state. That means there's no degeneracy pressure to save them. Instead, boson stars achieve stability through their wave-like nature. The overlapping quantum fields of the bosons create a kind of diffuse pressure, not by refusing to overlap, but by forming coherent oscillations that counteract gravity. Where neutron stars are upheld by the exclusion principle, Boson stars are upheld by collective quantum harmony. It's a striking contrast. Neutron stars, compact, dense, and structured around the rules of fermions. Gravity pulls inward, but neutron degeneracy pressure pushes back. They are supported by particles saying, "No, you can't occupy my state." Boson stars, potentially just as massive but governed by bosons. Gravity pulls inward, but the boson's wave functions spread outward, creating stability. They are supported by particles saying, "Yes, we can all occupy the same state together." Even their astrophysical signatures differ. Neutron stars often reveal themselves through pulsars, beams of radiation emitted from their rapidly rotating magnetic fields. We can detect them by their intense X-rays, gamma rays, and radio emissions. Boson stars, in contrast, would be silent. No fusion burns inside them. No degeneracy pressure sparks electromagnetic fireworks. They would lurk in the dark, betrayed only by how their gravity bends light or influences nearby matter. Another key difference lies in their limits. Neutron stars can only exist up to a certain mass, called the Tolman-Oppenheimer-Volkoff limit. If they exceed this threshold, roughly 2 to 3 times the mass of the Sun, not even neutron degeneracy pressure can resist gravity, and the star collapses into a black hole. Boson stars, however, don't follow this exact rule. Their stability depends on the mass of the bosons themselves. Ultralight bosons could form stars with galactic-scale radii, while heavier bosons could form stars denser than neutron stars but still stable. The rules of the game change entirely. This comparison highlights just how radical boson stars really are. Neutron stars are already among the strangest objects in the universe, yet we understand them within the framework of fermionic matter. Boson stars, by contrast, are exotic to the core, relying not on the exclusion principle but on the peculiar, collective behavior of bosons. Where neutron stars are built on resistance, boson stars are built on cooperation. In a way, the difference between neutron stars and boson stars captures a deeper truth about quantum mechanics itself. Fermions and bosons aren't just categories of particles, they are two opposite philosophies of existence. Fermions say, "I must be unique." Bosons say, "I will join the group." And in the universe, both philosophies lead to the creation of stars, one blazing in radio waves and X-rays, the other hidden in silence and gravity. The idea of boson stars isn't just a flight of imagination, it emerges directly from the mathematics of physics. At the heart of this lies Einstein's general relativity, the theory that describes how mass and energy warp space-time and how that curvature produces what we perceive as gravity. For more than a century, general relativity has been tested again and again. From the bending of starlight around the Sun to the detection of gravitational waves rippling across the cosmos. Its equations are incredibly rich, and depending on what kinds of matter or energy you include in them, they predict different kinds of astrophysical objects. Ordinary stars, neutron stars, and black holes all come out as solutions to Einstein's field equations when you account for matter made of fermions, radiation, and nuclear processes. But if you extend those same equations by adding a scalar field, something remarkable happens. New solutions emerge, ones that correspond to compact, self-gravitating objects not made of atoms at all. These are what we call boson stars. Let's unpack this step by step. Einstein's field equations relate the geometry of spacetime, the curvature described by the Einstein tensor, to the distribution of matter and energy, described by the stress-energy tensor. When the matter content is modeled as a perfect fluid, the way we describe gas and plasma inside normal stars, you get the family of stellar solutions we're familiar with. But suppose instead you insert into the equations a scalar field, a smooth distribution of bosonic particles described by a single value at each point in spacetime. Suddenly, the mathematics yields a whole new class of solutions. Stable, compact configurations of the scalar field bound together by gravity. These solutions were first worked out in the 1960s by physicist Donald Korp and later by Ruffini and Bonazola, who demonstrated that self-gravitating configurations of scalar fields could exist without collapsing. What makes this fascinating is that the equations don't require you to invent stability. It emerges naturally from the interplay of general relativity and quantum field theory. Gravity tries to squeeze the scalar field inward, while the quantum properties of the field, its oscillations and wave-like nature, push back. The balance is written directly into the mathematics. Mathematically, a boson star solution is a non-singular configuration, meaning it doesn't collapse into a black hole singularity but instead stabilizes at a finite size. These objects don't have an event horizon like a black hole, and they don't have a hard surface like a neutron star. Instead, they are smoothly distributed blobs of scalar field energy, tapering off into empty space. Their density peaks at the center and gradually decreases outward, but without any sharp boundary. This fuzziness is part of what makes them so elusive to detect. Even more intriguing, the equations suggest that boson stars can take on different forms depending on the properties of the bosons themselves. For example, if the bosons interact with one another, self-interacting scalar fields, the star's structure changes dramatically compared to the case where they don't. Different assumptions about the boson's mass, coupling strength, or self-interactions lead to different families of solutions. In fact, the range of possible boson stars is so broad that they could mimic other compact objects, appearing, from a distance, very much like neutron stars or even black holes. This mathematical foundation is critical because it shows that boson stars aren't just speculative what-ifs. They are embedded in the same equations that describe the Sun, neutron stars, and black holes. They are natural outcomes of extending those equations to include scalar fields, which we already know exist thanks to the Higgs boson. The open question is not whether the mathematics allows boson stars. It does, but whether nature has chosen to realize them in the actual universe. From a physicist's perspective, this is incredibly exciting. Boson stars represent a crossroads between two of the deepest theories we have: general relativity, which governs the cosmos on large scales, and quantum field theory, which governs particles on the smallest scales. By solving Einstein's equations with scalar fields, we find a possible meeting point of these two frameworks, a physical object that embodies both. If boson stars exist, they are not just astrophysical curiosities, they are physical evidence of how quantum fields and curved spacetime interact on stellar scales. And so, the mathematics tells us something profound. Given the right ingredients, gravity and a scalar field, the universe naturally allows boson stars. Whether or not we've seen them yet is another matter entirely, but their place in the equations is secure. They are not a product of fantasy. They are solutions written into the very fabric of general relativity once scalar fields are included. When we think of stars and planets, we instinctively imagine them as objects with surfaces. The Earth, for example, has a rocky crust beneath our feet. Jupiter, though made mostly of gas, still has a definable boundary where its atmosphere gives way to deeper layers. And even stars like the Sun, though made of plasma, present us with a surface known as the photosphere, the glowing layer that emits the light we see. These surfaces mark the boundaries where one physical state ends and another begins. But boson stars challenge this familiar notion. Unlike planets, neutron stars, or even ordinary stars, boson stars don't have a hard surface at all. Instead, they are composed of a scalar field, a smooth, wave-like distribution of bosons spread across space. Their density is highest at the center and gradually decreases as you move outward, tapering off into empty space without any sharp cutoff. There's no point where you can say, here is the edge of the star. This makes boson stars profoundly different from the stellar bodies we know. If you could approach one, which, of course, is purely hypothetical at this stage, you wouldn't find a place to stand or a glowing layer to touch. You'd simply pass through a region where the density of the bosonic field gets progressively stronger, peaks near the center, and then weakens again as you leave. It's almost like entering a fog. The boundaries are indistinct, and the intensity slowly changes without ever forming a solid wall. In contrast, consider a neutron star. A neutron star has an extremely well-defined surface. If you could somehow survive the crushing gravity and lethal radiation, you would encounter a crust only a few centimeters thick sitting on top of a sea of neutrons. The density jumps sharply at the boundary, making the star's surface distinct and abrupt. But in a boson star, no such boundary exists. The transition from inside to outside is smooth, continuous, and diffuse. This lack of a surface has major consequences for how boson stars might appear to us. For one, they would not emit light in the way that normal stars do. Without a photosphere, without any hot, glowing surface, there is nothing for them to radiate. They would be dark, transparent objects, detectable only by the way their gravity influences their surroundings. In fact, some simulations suggest that boson stars could be almost entirely invisible, blending into the cosmic background unless they pass in front of another source of light or disturb nearby stars and gas clouds. The absence of a surface also means that boson stars don't produce the violent phenomena we associate with other compact objects. When matter falls onto a neutron star, it slams into the solid crust, releasing enormous amounts of energy in the form of X-rays. When matter falls into a black hole, it builds up in a swirling accretion disk and heats to extreme temperatures as it spirals past the event horizon. But in the case of a boson star, there is no crust to crash into and no horizon to cross. Instead, infalling matter would pass through the diffuse bosonic cloud, interacting weakly with it, and potentially pass right out the other side. This could make boson stars appear ghostly compared to the dramatic fireworks of other compact objects. Some theorists have even speculated that this lack of a surface could allow boson stars to mimic black holes in certain ways. From a distance, if you measure only the gravitational pull, a massive boson star could appear indistinguishable from a black hole of similar mass. But unlike a black hole, a boson star would lack an event horizon. Instead of being swallowed irretrievably, matter and light could potentially escape, albeit deflected and distorted, after interacting with the scalar field. This makes distinguishing boson stars from black holes one of the key challenges for observational astrophysics. So, when we say boson stars don't have a hard surface, it's more than a quirky fact, it's a defining feature. It means they can't be directly seen in visible light. It means their interactions with matter are unlike those of any other stellar object. And it means they blur the line between inside and outside, existing as smooth, diffuse regions of quantum fields bound by gravity rather than as sharply defined balls of matter. This quality adds to the sense of mystery surrounding them. If such stars exist, they are not places we could ever land on or observe glowing in the sky. They would be silent, surfaceless shadows of stars, revealed only through the subtle curvature they imprint upon spacetime itself. One of the most mind-bending aspects of boson stars is their range of possible masses. Unlike ordinary stars, which are constrained by the processes of nuclear fusion and stellar evolution, boson stars are dictated almost entirely by the properties of the bosons that compose them, their mass, their interactions, and the way they form a self-gravitating quantum field. This means that boson stars could, in principle, exist across an extraordinary spectrum of sizes, from the minuscule to the cosmic. At the small end of the scale, boson stars could be tiny, as small as asteroids, or even smaller. If the bosons are relatively heavy particles, their quantum wave-like behavior would occur at very short scales. That means gravity could pull them together tightly, forming ultra-compact configurations. Such a boson star might have the mass of a mountain or a planet, compressed into a sphere the size of a grapefruit. These ultra-compact boson stars would be extremely difficult to detect because they would interact so little with normal matter, behaving almost like invisible rocks floating through space. Yet, their gravitational pull would be unmistakable if they passed near other objects. At the opposite extreme, boson stars could be massive, rivaling black holes in heft. If the bosons are ultralight particles, such as those theorized in some dark matter models, their wave-like nature would dominate across much larger distances. In this case, boson stars could stretch out to encompass entire star systems, or even mimic the gravitational influence of supermassive black holes found at the centers of galaxies. A boson star in this regime could weigh millions, or even billions, of solar masses, becoming a true cosmic heavyweight. From afar, such an object might look gravitationally identical to a supermassive black hole, yet it would lack an event horizon, making it fundamentally different. This astonishing flexibility in size comes down to a delicate interplay of gravity and quantum mechanics. The mass and radius of a boson star are not arbitrary but are directly tied to the mass of the boson itself. Heavier bosons produce smaller, denser stars, while lighter bosons produce larger, more diffuse ones. In fact, physicists sometimes talk about the boson star spectrum, a continuum of possible solutions to Einstein's equations with scalar fields. Depending on which boson nature has chosen, boson stars could populate the universe in ways that range from tiny, asteroid-sized lumps of invisible matter to colossal entities anchoring entire galaxies. This variability is part of why boson stars are so compelling as candidates for dark matter. If the universe is filled with ultralight bosons, then large boson stars could naturally form as gravitational clumps, blending into the large-scale structure of galaxies. If heavier bosons also exist, then smaller boson stars might drift invisibly through interstellar space, adding to the hidden mass budget of the cosmos. In either case, they could account for phenomena we currently ascribe to mysterious, unseen dark matter. It's also worth noting that this broad mass range makes boson stars versatile in how they might be observed, or at least inferred. Smaller boson stars could act as gravitational lenses, subtly bending light from background stars in a way similar to rogue planets or black holes. Larger ones could reveal themselves through their influence on galactic dynamics, possibly masquerading as the supermassive objects we believe sit at the hearts of galaxies. The flexibility in scale means that boson stars don't occupy a narrow niche. They could, in theory, exist at many different points across the cosmic hierarchy of structures. So when we say boson stars could be as small as asteroids or as massive as black holes, it isn't hyperbole. It's a reflection of the extraordinary freedom nature has in building these objects. Their sizes are dictated not by fusion, pressure, or ordinary matter, but by the fundamental properties of the particles that compose them. This makes them some of the most versatile and enigmatic objects in all of astrophysics, capable of hiding almost anywhere in the universe's grand architecture. When it comes to size, boson stars are unlike anything we've ever seen in the universe. Their scale is not fixed the way normal stars are. A star like our Sun is about 1.4 million kilometers across, while a neutron star compresses that mass into a sphere only about 20 kilometers in diameter. Those dimensions are set by well-understood processes like nuclear fusion, electron degeneracy, and neutron degeneracy. But boson stars obey a completely different set of rules, and their size depends almost entirely on the properties of the bosons themselves. Here's the extraordinary part. A boson star could be kilometers across, or, in the opposite extreme, it could be so compact that it's smaller than a single proton. This enormous range is possible because the size of a boson star is tied directly to the mass of the boson particle that composes it. Let's break this down. If the bosons are extremely light, such as the hypothetical actions many physicists believe could make up dark matter, their wave-like behavior extends across vast distances. When many of these particles cluster together under gravity, the quantum pressure that resists collapse spreads out over wide scales. The result? Boson stars that can be enormous, stretching across many kilometers, sometimes rivaling or exceeding the size of neutron stars. In these cases, a boson star would look like a diffuse, extended object with a gravitational pull spread out across space, almost like a mist of quantum fields condensed into a star-like form. On the other hand, if the bosons are relatively heavy, their wave functions are much more localized. That means the balance between gravity pulling inward and quantum effects pushing outward happens on much smaller scales. In this scenario, a boson star could shrink to minuscule proportions, unimaginably small, even smaller than the diameter of a proton, less than a femtometer. Such objects would pack stellar masses or smaller amounts of matter into a space tinier than anything in ordinary astrophysics. They would be invisible in the truest sense, compact beyond measure, detectable only through their gravitational influence. This radical size variability shows just how alien boson stars are compared to what we usually call stars. A star that can be kilometers wide or smaller than a proton is not really a star in the traditional sense at all, but rather a new category of astrophysical object defined by quantum fields and relativity. Now, this size dependence also has practical implications for how scientists might search for them. Larger boson stars, kilometers across, might reveal themselves through gravitational lensing, bending and distorting the light of background stars. They might also subtly influence the orbits of nearby stars or gas clouds in ways that telescopes like the James Webb Space Telescope or the European Extremely Large Telescope could one day measure. Smaller boson stars, however, present a completely different challenge. If one is smaller than a proton, how could we possibly detect it? The only way would be through highly sensitive gravitational wave detectors or by looking for unusual disturbances in the motion of astrophysical systems. Another point worth noting, this incredible range in size is not just an odd fact about boson stars, it's a window into fundamental physics. By measuring or constraining the possible sizes of boson stars, scientists can indirectly probe the properties of the bosons themselves. If boson stars turn out to be kilometers across, That suggests ultralight bosons dominate. If they are extremely compact, that points to heavier bosons. In either case, their size becomes a cosmic clue, offering insight into the fundamental building blocks of nature. So, when we say boson stars could be as large as kilometers or smaller than a proton, we're not exaggerating, we're highlighting the sheer strangeness of these objects. They stretch the imagination of scale to its very limits, existing in a spectrum that ranges from the macroscopic to the subatomic. They remind us that in the universe, size is not always constrained by familiar rules, and that the fabric of reality may harbor objects beyond anything we've ever conceived. One of the defining traits of stars, as we commonly understand them, is their light. When you look up at the night sky, every twinkling point is a star blazing across unimaginable distances. Our sun, too, is a radiant furnace, constantly pouring out energy in the form of visible light, ultraviolet rays, infrared heat, and more. This light originates from nuclear fusion, the process of smashing hydrogen atoms into helium deep in the stellar core. Fusion releases enormous amounts of energy, and it's this energy that makes stars shine so brightly. Boson stars, however, flip this idea on its head. They don't shine at all, not in visible light, not in X-rays, not even in infrared. They are, by their very nature, dark. Why? Because inside a boson star, there is no nuclear fusion happening. There are no protons or neutrons or electrons colliding at high temperatures to ignite thermonuclear reactions. Instead, the star is composed entirely of bosons in a collective quantum state. These bosons don't generate heat through collisions or nuclear processes. They simply form a stable, self-gravitating field held together by the balance of quantum pressure and gravity. This absence of fusion has profound consequences. First, it means boson stars do not behave like ordinary stars at all. They don't produce the kind of electromagnetic radiation that lights up galaxies. They don't generate solar winds or bathe nearby planets in life-sustaining energy. If the Sun were a boson star, Earth would be a frozen wasteland, cloaked in eternal night. In fact, if boson stars exist, they are invisible to traditional telescopes that rely on capturing light, whether in the visible spectrum or in other wavelengths. Second, their lack of light makes them nearly indistinguishable from empty space. This is one reason they are considered candidates for dark matter. They exert gravitational influence, but they don't radiate. They are mass without glow, presence without visibility. Their stealthy nature makes them elusive, requiring astronomers to search for indirect signatures, such as gravitational lensing effects or unusual motions of stars near their gravitational fields. Contrast this with neutron stars or white dwarfs, which, though they no longer sustain fusion, still glow faintly from residual heat or from accreting material. Even black holes, which emit no light from within their event horizons, announce themselves dramatically through the radiation of the hot, swirling accretion disks that feed them. Boson stars, by comparison, are silent and invisible, with no accretion disks, no hot surfaces, and no bursts of radiation. Their only footprint is the way they bend spacetime itself. This characteristic makes boson stars doubly fascinating. On one hand, their invisibility means they could be lurking throughout the cosmos, hidden in plain sight, blending seamlessly into the cosmic background. On the other hand, their lack of light forces us to rethink what it means to call something a star. For thousands of years, stars have been synonymous with light. The very word star conjures images of radiance, heat, and illumination. Boson stars strip away that assumption and redefine the category. They are stars not because they shine, but because they are self-gravitating, stable configurations of matter, or, more precisely, of fields. And here lies an almost poetic irony. Boson stars, though they themselves are dark, may hold the key to illuminating one of the greatest mysteries in science, the true nature of dark matter and the fundamental building blocks of reality. They are paradoxes in astrophysical form, stars that don't shine, lightless objects that may ultimately reveal the most profound truths about the universe. If ordinary stars are the universe's lanterns, then boson stars are its phantoms. Their most unsettling feature is their transparent nature, the idea that they could be almost completely invisible to us, leaving no glow, no shadow, and no trace except for the way their gravity alters the space around them. Why would they be transparent? The answer lies in their makeup. Boson stars are not built from protons, neutrons, or electrons. the building blocks of ordinary matter. They are composed entirely of bosons, which can all collapse into the same quantum state, overlapping like a perfectly synchronized choir of particles. This collective state doesn't interact with light in the way that atoms do. Atoms have electrons that absorb and emit photons, creating the familiar glow of stars, the reflection of planets, and even the colors we see on Earth. Bosons in a boson star don't have this mechanism. Without charged particles and without nuclear fusion, there's nothing inside a boson star that can grab onto photons. Light would simply pass straight through, as if the object weren't even there. Imagine staring through a region of space where a boson star resides. You wouldn't see a dark blot blocking the stars behind it, as you might with a dense cloud of gas or dust. Instead, the background stars would appear almost perfectly normal, except for subtle distortions caused by gravitational lensing. The boson star itself would remain utterly transparent, like a glass sphere suspended in space. This near invisibility is what makes boson stars such tantalizing candidates for dark matter. Dark matter is defined by what it does not do. It doesn't emit light, it doesn't absorb light, and it doesn't scatter light. In other words, it's invisible, detectable only by its gravitational effects. Boson stars fit this description perfectly. They could be scattered across galaxies, adding mass and gravitational pull, but remain unseen because photons slip through them without interaction. The implications are staggering. If boson stars are real, they could be hiding in plain sight all around us, woven into the structure of galaxies, even drifting through the Milky Way itself. They wouldn't darken the sky or obscure our view of distant objects. Instead, they would ghost silently through space, indistinguishable from emptiness except for the way they bend the paths of passing starlight or tug ever so slightly on the orbits of nearby stars. But their transparency isn't absolute in every situation. While light may not scatter inside a boson star the way it does in normal matter, gravity still leaves a telltale mark. Photons traveling near a boson star would have their paths bent, a phenomenon known as gravitational lensing. To an observer, this could make background stars appear distorted, magnified, or even multiplied. In fact, gravitational lensing is one of the most promising methods astronomers have for detecting such elusive objects. A boson star itself wouldn't glow, but the warped image of another star shining behind it could betray its presence. This transparent nature also means that boson stars blur the line between something and nothing. Normally, when we think of an object, we think of something that blocks light, casts a shadow, or emits radiation. Boson stars do none of these things. They are objects only in the sense that their mass curves space-time and influences the movement of other bodies. In every other respect, they masquerade as void. It's almost eerie to imagine a star-sized object drifting silently through a galaxy, exerting the gravity of millions of suns, yet completely unseen to human eyes. If one were to pass near our solar system, it wouldn't light up our sky or cast a glow on our planets. It would arrive and depart like a ghost, disturbing orbits and bending starlight, but otherwise leaving no visible sign of its passage. So when we describe boson stars as transparent, we mean it literally. They do not block, absorb, or emit light. They are invisible entities, their existence betrayed only by the subtle fingerprints of gravity. And in that way, they stand as perfect symbols of the universe's greatest mystery, unseen matter shaping everything we know. One of the most intriguing consequences of the invisible, transparent nature of boson stars is their ability to bend light through gravitational lensing. Even though these stars do not emit any light themselves, their gravity can profoundly affect the path of photons traveling nearby, revealing their presence indirectly. This phenomenon is a direct consequence of Einstein's general relativity, which tells us that mass and energy warp the fabric of space-time. Light, while massless, travels along these curves, meaning that anything massive can act like a lens, bending and distorting the light of objects behind it. Gravitational lensing is not a new concept. It has been observed countless times in astronomy. Massive galaxies and galaxy clusters can bend the light from even more distant galaxies, producing arcs, rings, or multiple images. This effect has become a crucial tool for mapping dark matter, because we can see its influence on light even if we can't detect the dark matter directly. Boson stars, despite being completely transparent, would have a similar effect, but on smaller scales. The intensity of gravitational lensing depends on the mass and compactness of the boson star. A relatively small, asteroid-mass boson star would produce only subtle distortions, perhaps slightly shifting the apparent position of a background star. Such microlensing events could, however, be detected by precise astronomical surveys, such as OGLE, Optical Gravitational Lensing Experiment, or Gaia, which track the positions and brightness of millions of stars over time. On the other hand, a massive boson star, perhaps rivaling the mass of a black hole, could bend light dramatically, producing lensing patterns that mimic those of black holes or neutron stars. This lensing effect also offers a tantalizing way to distinguish boson stars from other compact objects. Unlike a black hole, which has an event horizon that traps light, a boson star has no hard surface and no horizon. Light passing near a boson star can be bent without being swallowed. In theory, this could produce unique lensing signatures, subtle deviations in the paths of photons that might allow astronomers to differentiate a boson star from a black hole of similar mass. In practice, this is extremely challenging, but it provides a concrete observational handle on these otherwise invisible objects. The shape and characteristics of the lensing also depend on the internal structure of the boson star. Because their density is highest at the center and gradually falls off, the gravitational field changes smoothly with radius. This creates a lensing profile that differs from the sharp cutoff of a black hole or the more abrupt density profile of a neutron star. A background star passing behind a boson star could appear slightly stretched or distorted in ways that encode information about the star's mass and the properties of its constituent bosons. Gravitational lensing also has implications for studying dark matter. Since boson stars are candidates for dark matter, their lensing could help map the distribution of this elusive substance in galaxies. If astronomers observe microlensing events in regions where no visible matter exists, it could be a hint that boson stars are lurking there. By analyzing the lensing patterns, researchers could infer the mass, size, and frequency of these objects, providing indirect but powerful evidence of their existence. Interestingly, boson stars could also produce more exotic lensing phenomena, such as Einstein rings or multiple images of a single background source, depending on their alignment with the observer and the distant object. In some cases, the light from a single star could be split into several images, creating arcs or even a faint halo effect. This would be a striking, albeit rare, signature of a boson star in action. So even though boson stars are completely dark and transparent, their gravitational influence acts as a kind of cosmic spotlight. They cannot shine themselves, but they reveal themselves through the bending of light around them. In this way, gravitational lensing provides a rare and invaluable tool to detect these elusive, invisible stars, turning what seems like empty space into a subtle laboratory for studying the deepest mysteries of quantum fields and dark matter. Another way boson stars could make themselves known, despite being completely invisible to light, is through their influence on the motion of nearby stars and gas clouds. Even though we cannot see a boson star directly, its gravity can leave unmistakable fingerprints on its surroundings, subtly altering orbits and trajectories in ways that reveal its presence. Gravity is the universal messenger in this case. Any massive object, whether luminous or dark, exerts a gravitational pull that nearby stars and gas clouds must obey. If a boson star drifts through a star cluster or lies within a galactic halo, it will affect the motion of any nearby celestial bodies. Stars may speed up, slow down, or deviate from expected orbital paths, while gas clouds might compress or spiral unexpectedly. Over time, these deviations can provide astronomers with clues that a massive, unseen object is lurking nearby. This method of detection is not just hypothetical, it's based on techniques already used to infer the presence of dark matter and exoplanets. For instance, astronomers can map the motion of stars in the outskirts of galaxies and notice discrepancies between observed velocities and those predicted by visible matter alone. Some of these discrepancies have already pointed to the presence of dark matter. Boson stars, if present, would contribute to such deviations, providing localized regions of enhanced gravitational influence. Consider a globular cluster, a dense, spherical collection of stars orbiting a galaxy. If a boson star moves through or resides within the cluster, its gravity could subtly pull on the stars, slightly altering their velocities. Over time, astronomers could detect unusual accelerations or orbital patterns inconsistent with the cluster's known stellar mass distribution. These anomalies would be subtle, but precise measurements of stellar motions, such as those being carried out by the Gaia satellite, could potentially identify them. Similarly, gas clouds in galaxies are highly sensitive to gravitational disturbances. If a boson star passes nearby, its gravitational pull could compress the gas, inducing shocks, turbulence, or unusual rotation patterns. Astronomers studying galactic gas dynamics with radio or millimeter wave telescopes could, in principle, detect these anomalies. Because boson stars have no hard surface and no radiation, their gravitational effects would be the only sign of their presence. Another scenario involves boson stars orbiting the centers of galaxies, possibly even masquerading as supermassive black holes. In this case, the motion of stars in close proximity, such as the famous S-stars orbiting Sagittarius A at the Milky Way's core, could reveal subtle discrepancies if a boson star were present instead of a black hole. The orbits might still appear Keplerian in general, but tiny deviations from predictions could betray the star's fundamentally different structure and lack of an event horizon. Stellar motion clues offer one of the most promising avenues for detecting boson stars because they rely on gravity rather than light. Light is irrelevant to these stars. Photons pass straight through them. But mass bends spacetime, and stars, gas, and dust faithfully respond. Careful mapping of stellar velocities and trajectories could uncover objects that are otherwise entirely hidden, providing an indirect but powerful method of detection. This method also scales across the mass spectrum of boson stars. Small, asteroid-sized boson stars might only perturb the motion of nearby stars slightly, requiring extremely precise measurements to detect. Larger, more massive boson stars could dominate the gravitational environment of an entire cluster or dwarf galaxy, leaving much more noticeable signatures. By combining observations across different scales, astronomers could potentially build a map of where these invisible objects reside and even infer the properties of the bosons that make them up. In essence, boson stars could be ghostly puppeteers, invisible to the eye but clearly moving the strings of their cosmic neighborhood. By observing how stars and gas respond to unseen forces, scientists may be able to infer not only the presence of these mysterious stars but also their mass, distribution, and even the quantum properties of the particles that compose them. Stellar motion, then, becomes a natural detective, revealing the hidden actors in the universe's grand play. One of the most exciting prospects for detecting boson stars lies in gravitational waves, ripples in spacetime first predicted by Einstein and detected a century later by LIGO. Gravitational waves are generated by massive objects accelerating or colliding, and they carry information about the dynamics, masses, and internal structures of those objects. While black holes and neutron stars have already produced detectable gravitational wave signals, boson stars could generate waves with entirely unique signatures, offering a new window into the universe's hidden population of exotic stars. When two boson stars approach each other, their gravitational fields interact in complex ways. Unlike black holes, which are essentially featureless points of mass surrounded by an event horizon, boson stars are extended objects with a diffuse distribution of mass. This means the merger dynamics are fundamentally different. As the stars spiral toward one another, their overlapping scalar fields interact, creating oscillations and distortions in the combined quantum field. These interactions can imprint distinctive features onto the emitted gravitational waves, potentially making them distinguishable from those generated by black hole or neutron star mergers. The waveform of a boson star merger is expected to show more gradual in spirals and a potentially longer merger phase than black holes. Black holes, being extremely compact and lacking a hard surface or internal structure, merge in a sharp, high-amplitude burst of gravitational waves followed by a brief ringdown as the newly formed black hole settles. Boson stars, on the other hand, can partially pass through each other because their fields overlap rather than collide like hard matter. This could produce gravitational wave signals that are smoother, more prolonged, and possibly modulated with oscillatory patterns reflecting the underlying scalar field interactions. Additionally, depending on the mass and self-interaction strength of the bosons, the merged object could undergo oscillations or breathing modes that persist for longer than the typical black hole ringdown. These oscillations would continue radiating gravitational waves until the system stabilizes. This gives physicists a potential signature that could be used to identify boson stars in gravitational wave data. Unlike black holes, whose ringdowns are predictable and universal, boson star mergers might produce a wide variety of waveforms depending on the internal structure of the stars, their masses, and the properties of the scalar fields. Another intriguing possibility is that some boson star mergers might avoid collapsing into black holes entirely, even at high combined masses. This contrasts sharply with neutron stars, which have a maximum mass limit, and black holes, which are inevitable when the combined mass exceeds a threshold. If two boson stars merge without forming a black hole, they could create a massive, oscillating boson star that continues to radiate gravitational waves for extended periods, potentially observable as a prolonged signal. Gravitational waves from boson star mergers could also provide a direct probe of the underlying particle physics. The frequency, amplitude, and duration of the waves would depend on the mass of the bosons and the strength of their self-interactions. Detecting these waves would not just confirm the existence of boson stars, it would provide experimental constraints on the properties of ultralight particles that are otherwise nearly impossible to study in terrestrial laboratories. In other words, gravitational waves could allow us to study the quantum world on a cosmic scale. Simulations of boson star collisions suggest that the emitted gravitational waves may look superficially similar to black hole mergers, but careful analysis of the waveform structure could reveal discrepancies. Features such as extended merger phases, oscillatory post-merger signals, or deviations from expected amplitudes could all serve as indicators of the presence of boson stars. Scientists are already developing models to predict these waveforms, with the hope that future observations might reveal their unique fingerprints. In summary, merger signals offer one of the most promising avenues for detecting boson stars. Unlike conventional stars, boson stars are invisible in light, but when they collide, they announce themselves loudly in spacetime itself. Gravitational waves from these collisions could reveal their mass, structure, and even the properties of the bosons they are made of, providing a revolutionary new method for studying exotic forms of matter and dark matter candidates. If detected, these signals would not only confirm the existence of boson stars but also open a window into a completely new realm of physics. The exciting potential of detecting boson stars through gravitational waves naturally raises the question: could we actually observe them with current technology? The answer is increasingly optimistic. Observatories like LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo were originally designed to detect mergers of black holes and neutron stars, but their sensitivity extends to a wide range of gravitational wave sources, including those predicted for boson star collisions. LIGO and Virgo work by measuring incredibly tiny distortions in spacetime, changes as small as a fraction of the diameter of a proton, caused by passing gravitational waves. These instruments are so precise that they can detect events billions of light-years away. When two massive objects like black holes merge, they produce gravitational waves strong enough for LIGO and Virgo to pick up. The question is whether boson star mergers produce waves within the same detectable range. Simulations suggest that the answer is yes, at least in many cases. The gravitational waves from boson star mergers could be slightly different in form, but still comparable in amplitude to those produced by neutron stars or smaller black holes. Their longer in-spiral phases and oscillatory post-merger signatures would be captured by the observatories, provided the stars are close enough and massive enough. In fact, some scientists argue that LIGO and Virgo may have already detected signals that could include boson star candidates, but without a distinct theoretical template for these events, they may have been misidentified or attributed to unusual black hole mergers. This is where the development of waveform templates becomes crucial. LIGO and Virgo don't just detect raw gravitational waves, they detect patterns that match theoretical predictions. For black holes and neutron stars, we have highly accurate templates. For boson stars, physicists are actively creating models that account for the unique dynamics of scalar fields, the extended mass distributions, and possible oscillations during and after the merger. Once these templates are incorporated into the analysis pipelines, it becomes possible to search existing data for previously unrecognized boson star events. Interestingly, boson star mergers could also produce distinctive frequencies in the gravitational wave spectrum. The precise frequencies depend on the mass of the bosons and the size of the stars, meaning that LIGO and Virgo could, in principle, not only detect a boson star merger but also provide constraints on the properties of the underlying particles. This would be groundbreaking. It would allow astrophysicists to study particle physics using a cosmic laboratory rather than a particle accelerator. In addition to LIGO and Virgo, future gravitational wave detectors promise to expand our observational reach. The upcoming LISA, Laser Interferometer Space Antenna, mission planned for the 2030s, will be sensitive to lower frequency waves, opening the door to detecting massive boson star mergers across galactic scales. Ground-based upgrades like LIGO A+ and Cosmic Explorer will increase sensitivity and precision, improving the chances of distinguishing boson stars from other compact objects. The possibility that we might already have the capability to detect boson stars is thrilling because it means that these exotic objects could move from theory to reality within our lifetimes. Unlike many speculative astrophysical objects that require next-generation instruments, boson stars are, in principle, within the reach of current observatories, provided we know what to look for. Every gravitational wave detection could harbor a hidden signature of boson star physics, waiting to be decoded. So, the LIGO and Virgo networks don't just represent a tool for confirming Einstein's theory of general relativity. They could also serve as our first real opportunity to observe these invisible, enigmatic stars. By capturing the faint ripples of spacetime generated during boson star mergers, these detectors might allow us to confirm the existence of entirely new forms of matter and uncover one of the universe's most profound secrets: the nature of dark matter and the role of scalar fields in shaping cosmic structure. One of the most compelling reasons boson stars capture the imagination of astrophysicists is their potential connection to dark matter halos, the mysterious, invisible scaffolding that holds galaxies together. Observations of galaxies have long shown that the visible matter, stars, gas, and dust, cannot account for the gravitational forces required to keep galaxies from tearing themselves apart. Something unseen, something massive, must be present, forming what we call a dark matter halo. Could boson stars, those invisible, surfaceless objects, be part of this hidden structure? The answer might well be yes. Boson stars, depending on the mass of the bosons and how they cluster, could form compact or extended clumps of matter that are effectively invisible to traditional telescopes. Because they do not emit light and interact very weakly with normal matter, they perfectly match the defining characteristics of dark matter. Unlike ordinary stars, which radiate energy and interact electromagnetically, boson stars would drift silently through the galactic halo, influencing the motion of stars, gas, and dust only through gravity. Imagine a galaxy like the Milky Way. Its visible disk, full of stars and gas clouds, is embedded within an enormous halo of dark matter that extends far beyond the reach of ordinary light. If boson stars are present, they could constitute a significant fraction of this halo, forming a network of gravitationally bound objects that collectively shape the galaxy's rotation curve. Each individual boson star may be tiny or massive, but together, they could account for the missing mass astronomers have inferred from stellar motions. There are several ways boson stars could populate a dark matter halo. Some might form in the early universe from primordial scalar field fluctuations, collapsing under their own gravity into small but dense objects. Others could grow through mergers and accretion, forming more massive boson stars over cosmic time. This hierarchical structure could naturally produce the clumpy, extended halos that simulations suggest are necessary to explain observed galactic dynamics. One striking implication is that boson stars could help resolve some of the lingering problems in dark matter theory. Standard models of cold dark matter predict a very smooth halo at large scales, but observations show that some galaxies have clumpy or cuspy distributions of dark matter. A population of boson stars, each acting as a dense, localized concentration of dark matter, could naturally explain these clumps without invoking exotic interactions or modifications to gravity. Their distribution would be determined by the dynamics of the early universe and subsequent galactic evolution, leading to a rich and varied halo structure. Moreover, boson stars in dark matter halos could produce observable gravitational effects that reveal their presence. They might slightly alter the rotation curves of stars in the outer regions of galaxies, create subtle gravitational lensing events as they pass in front of background objects, or perturb globular clusters and satellite galaxies. These effects would be faint and challenging to detect, but careful surveys and precise measurements could potentially uncover patterns consistent with a halo composed, at least in part, of boson stars. There's also a tantalizing theoretical connection. The ultralight bosons thought to form boson stars are precisely the kinds of particles proposed in some dark matter models, such as actions. If these particles dominate the dark matter content of the universe, boson stars could be natural condensations of this dark matter, forming coherent structures instead of remaining as a diffuse, featureless background. This would provide a direct link between particle physics and galactic astrophysics, connecting the tiniest scales of quantum fields to the largest scales of galaxy formation. In short, boson stars could act as the building blocks of dark matter halos, quietly shaping the structure and dynamics of galaxies without ever revealing themselves through light. They would provide the gravitational glue that holds stars in orbit, explains anomalous rotation curves, and contributes to the unseen mass inferred by astronomers. Their presence in galactic halos would transform our understanding of dark matter from a uniform, invisible medium into a population of exotic, gravitationally bound stars, bridging the gap between astrophysics and fundamental particle physics. By considering boson stars as constituents of dark matter halos, we gain a unifying picture: invisible, transparent, quantum objects, obeying different physics than ordinary stars, yet exerting profound influence over cosmic structures. They would be both everywhere and unseen, shaping the universe silently while eluding traditional observational techniques, a perfect candidate for one of the universe's greatest mysteries. Another tantalizing possibility arises when we consider the cores of galaxies, especially the supermassive objects thought to reside there. For decades, astronomers have assumed that the centers of most large galaxies, including our own Milky Way, harbor supermassive black holes, objects millions to billions of times the mass of the Sun, with gravitational pulls so strong that not even light can escape. But what if some of these mysterious cores aren't black holes at all? What if, in certain cases, they are actually boson stars? At first glance, this might seem improbable. Black holes dominate astrophysical thinking because of their distinct gravitational signatures, extreme compactness, the bending of light near their event horizons, and, in the case of active black holes, the intense radiation from accretion disks. However, boson stars, particularly massive ones formed from ultralight bosons, could mimic many of these gravitational effects. Because they can accumulate tremendous mass, their gravity could influence nearby stars and gas in ways very similar to a black hole, producing rotation curves and orbital dynamics that are nearly indistinguishable from what we expect around a true event horizon. The key difference lies in the structure and absence of an event horizon. Black holes are defined by a singularity at their center and an event horizon from which nothing escapes. A boson star, by contrast, has no singularity, no surface, and no horizon. Its mass is spread across a region of space, with the highest density at the center, tapering smoothly outward. For a distant observer measuring stellar orbits, this extended mass distribution could produce nearly the same gravitational pull as a black hole, particularly if the boson star is very compact. The supermassive object at the center of the Milky Way, Sagittarius A, provides a useful example. Observations of stars orbiting very close to this core have been interpreted as proof of a supermassive black hole, largely because of the high velocities and tight orbits. But a sufficiently compact boson star could, in principle, generate the same orbital dynamics, while leaving one critical difference: light and matter that approach it might behave slightly differently than they would near a black hole's event horizon. There would be no point of no return. Photons could pass through or around the boson star rather than being trapped irretrievably. Another clue comes from the absence of certain emissions. Some galactic cores that appear massive yet lack strong accretion signatures might be better explained by boson stars. Because boson stars have no hard surface, infalling matter wouldn't slam into a crust or generate high-energy radiation in the same way it would near a neutron star. And unlike black holes, where infalling matter heats up dramatically before crossing the event horizon, boson stars would allow matter to pass through their diffuse field, producing subtler or more distributed emissions. In some cases, this might explain cores that appear dark despite their mass. Theoretical studies suggest that boson stars could exist with masses rivaling those of supermassive black holes, stretching over scales of astronomical units or more, depending on the particle mass of the constituent bosons. In these cases, a boson star could occupy the galactic core and remain virtually invisible in light, yet dominate the gravitational landscape. Observing the fine details of star motions near the galactic center, or analyzing gravitational waves from interactions near these cores, could eventually distinguish between a true black hole and a massive boson star. If even a fraction of supermassive objects in galactic cores were boson stars, it would revolutionize our understanding of galaxy formation and evolution. Black holes are thought to regulate star formation, influence the growth of galaxies, and drive feedback processes through powerful jets. Boson stars, with different internal physics, could produce alternative evolutionary pathways. For instance, galaxies hosting boson stars instead of black holes might show subtle differences in star formation rates, gas dynamics, or the behavior of surrounding matter. This possibility also underscores the observational challenge. Boson stars in galactic cores would be nearly invisible, detectable only through the motions of nearby stars, gravitational lensing, or potentially, subtle gravitational wave emissions. High-precision instruments, like the Event Horizon Telescope, which recently captured the shadow of M87, might eventually be able to detect deviations in the expected shape or size of a shadow, hinting that what appears to be a black hole is actually a dense boson star. In essence, galactic cores present a tantalizing frontier for boson star research. These invisible giants could be hiding in plain sight at the hearts of galaxies, masquerading as black holes while subtly betraying their existence through nuanced gravitational effects. Confirming their presence would not only rewrite our understanding of galactic centers but also provide direct evidence of exotic quantum fields playing a dominant role on cosmic scales. A critical question when studying boson stars is whether they are stable over cosmic timescales. After all, the universe has existed for over 13 billion years, and any object that fails to maintain its structure for a significant fraction of that time would be unlikely to play a meaningful role in astrophysics or dark matter. Understanding the stability of boson stars is therefore central to determining whether they could exist in large numbers today and influence galactic dynamics. Stability in this context depends on a delicate balance between gravity and quantum effects. Gravity constantly pulls matter inward, attempting to collapse the star into an ever denser configuration. In ordinary stars, stability comes from a combination of thermal pressure, from fusion, and degeneracy pressure, for compact objects like white dwarfs and neutron stars. Boson stars, however, do not rely on thermal pressure or conventional degeneracy pressure. Instead, their stability is governed by the quantum nature of the bosons themselves, particularly the wave-like behavior of the scalar fields. Bosons, unlike fermions, are allowed to occupy the same quantum state. This creates a collective wave function describing the boson star as a whole. The quantum pressure arises from the uncertainty principle. Confining the bosons too tightly increases their momentum and energy, generating an effective outward force that resists gravitational collapse. In mathematical terms, this balance is encoded in the solutions to Einstein's equations with scalar fields. These solutions indicate that boson stars can indeed maintain stable configurations, where inward gravity is countered by the outward pressure of the quantum wave function. However, stability is not guaranteed for all boson star configurations. The mass of the constituent bosons plays a key role. Lighter bosons tend to produce larger, more diffuse stars that are generally stable over long periods. Heavier bosons produce smaller, denser stars, which may be more prone to instabilities. If a boson star accumulates too much mass, it could collapse under its own gravity, potentially forming a black hole. This is analogous to the Tolman-Oppenheimer-Volkoff limit for neutron stars, where exceeding a maximum mass leads to catastrophic collapse. For boson stars, the maximum stable mass depends on both the boson mass and any self-interaction terms in the scalar field. Self-interactions among the bosons add another layer of complexity. Attractive self-interactions can destabilize a boson star, making it easier to collapse, while repulsive interactions can enhance stability, allowing the star to exist at higher masses. Some theoretical models even predict oscillating or quasi-stable configurations, where the star maintains overall coherence while experiencing small, persistent fluctuations in density. These oscillations may slowly radiate energy away as gravitational waves, but not enough to destroy the star, enabling it to persist for billions of years. Numerical simulations of boson star dynamics further reinforce their potential stability. Many models show that boson stars can survive perturbations such as nearby gravitational disturbances, collisions with other stars, or accretion of additional bosons, without collapsing or dispersing. This robustness is crucial because, in a realistic galactic environment, no object exists in complete isolation. A stable boson star must withstand tidal forces, interactions with other dark matter clumps, and other astrophysical processes. Simulations suggest that boson stars are remarkably resilient, particularly for configurations dominated by ultralight bosons. Yet, there are limits. Extremely massive or dense boson stars may be prone to collapse into black holes if perturbed beyond a critical threshold. Similarly, Collisions between boson stars could destabilize one or both objects, producing gravitational waves and potentially leaving behind a single, larger star or a black hole. These processes introduce dynamical evolution over cosmic timescales, meaning that while boson stars are generally stable, their population and structure in the universe might evolve slowly over billions of years. Ultimately, the consensus among theorists is that boson stars can be stable over cosmological timescales, particularly if the bosons are light and/or repulsively interacting. Their longevity is one of the reasons they are considered viable candidates for dark matter, as they could have formed in the early universe and persisted to the present day, quietly shaping the gravitational architecture of galaxies without ever being seen. In short, the stability of boson stars arises from the interplay of quantum mechanics and gravity. While extreme configurations can collapse, the vast majority of plausible boson star models suggest that these exotic objects are long-lived, resilient, and capable of existing throughout cosmic history, making them not just theoretical curiosities but potentially enduring constituents of the universe. Boson stars, while fascinating in their own right, become even more intriguing when we consider their potential for exotic interactions. Unlike ordinary stars, which follow well-charted evolutionary pathways, boson stars exist in a domain where quantum mechanics and general relativity intersect, allowing for possibilities that challenge our conventional understanding of astrophysical processes. Among these possibilities are mergers, transformations, and even collapses into black holes. One of the simplest exotic interactions to imagine is the merger of two boson stars. Unlike neutron stars or ordinary stars, boson stars lack a hard surface, meaning that when they collide, their constituent fields can overlap smoothly. This passing through behavior, a consequence of the boson's ability to occupy the same quantum state, leads to a merger process fundamentally different from the violent collisions of conventional stars. The resulting object could be a larger boson star, oscillating as the overlapping fields settle into a new equilibrium. These oscillations may radiate energy in the form of gravitational waves, potentially detectable by instruments like LIGO, providing a direct observational signature of the merger. However, not all mergers are benign. If the combined mass of the merging boson stars exceeds a critical threshold, gravitational collapse into a black hole becomes inevitable. This threshold is determined by the mass of the bosons and any self-interactions in the scalar field. For light, weakly interacting bosons, the threshold mass can be enormous, allowing supermassive boson stars to exist. For heavier or more strongly interacting bosons, the critical mass is lower, meaning that relatively modest mergers could trigger collapse. In this way, boson star interactions could contribute to the population of black holes in the universe, suggesting a dynamic interplay between exotic stars and more familiar compact objects. Beyond mergers, boson stars might undergo transformations into different states under extreme conditions. For instance, a boson star accumulating additional mass from its surroundings might gradually evolve from a lower density configuration into a denser one. Similarly, interactions with other boson stars or high-energy astrophysical events could excite the star into higher energy states, temporarily altering its density profile or oscillation patterns. These changes might affect its gravitational footprint, leading to subtle but observable consequences in nearby stellar motions or gravitational wave emissions. There is also speculation about transmutation between boson stars composed of different particle species. In some models of particle physics, multiple types of bosons may coexist, and under certain conditions, one species could convert into another via interactions predicted by quantum field theory. If boson stars contain multiple species, interactions between them could lead to phase transitions, transforming the internal structure of the star without collapsing it entirely. These transformations could manifest as shifts in size, mass distribution, or oscillatory behavior, adding another layer of complexity to their evolution. Another fascinating possibility involves boson star-black hole interactions. A boson star passing near a black hole could be tidally disrupted, losing mass as its outer regions are stripped away. Conversely, a boson star could merge with a black hole, adding to its mass in a way that might produce distinctive gravitational wave signatures, different from the merger of two black holes. Such interactions blur the distinction between boson stars and conventional compact objects, highlighting their role as both independent entities and contributors to the population of black holes. These exotic interactions also tie directly to cosmological implications. If boson stars can merge, collapse, or transform, they may participate in the formation of massive objects in the early universe. Clusters of boson stars could combine to form larger structures, contributing to the assembly of supermassive black holes or influencing the distribution of dark matter in galaxies. Their long-term evolution could thus shape the large-scale structure of the universe in ways that are subtle yet profound. In short, boson stars are not static curiosities. They are dynamic, interacting objects capable of mergers, collapses, oscillations, and transformations. These behaviors are dictated by the interplay of gravity, quantum effects, and the properties of the constituent bosons. Observing such interactions, particularly through gravitational waves, could provide unparalleled insight into both the nature of exotic matter and the processes that govern the universe's hidden mass. Boson stars matter. In fact, they could be one of the keys to solving one of the biggest mysteries in physics and cosmology, the nature of dark matter. Dark matter comprises roughly 27% of the universe's total mass-energy content, yet we have never observed it directly. Its presence is inferred only through its gravitational effects, the way it holds galaxies together, bends light via gravitational lensing, and influences the cosmic web's large-scale structure. Despite decades of experimental searches for dark matter particles, its true identity remains elusive. Boson stars could offer a bridge between theory and observation. At their core, boson stars are hypothesized to be made of ultralight bosons, potentially the very particles that make up dark matter. If these bosons exist and are abundant in the universe, they could naturally form boson stars, clumping under gravity into structures that behave like localized concentrations of dark matter. Unlike ordinary stars, which are luminous and composed of familiar atoms, boson stars would be invisible, their presence felt only through gravity. This matches the defining properties of dark matter, making them a plausible candidate not just for isolated exotic objects, but for an integral component of the cosmos' unseen mass. Studying boson stars could also help us probe the properties of these hypothetical particles. Observing a boson star through gravitational lensing, stellar motion, or gravitational waves provides data about its mass, size, and internal structure. These parameters are directly tied to the mass of the constituent bosons and their interactions. In other words, by studying the macroscopic astrophysical properties of boson stars, scientists can gain insight into the microscopic physics of dark matter particles, a remarkable intersection of quantum theory and astrophysics. Furthermore, boson stars could reveal the distribution and behavior of dark matter on multiple scales. Large boson stars might reside in galactic cores, mimicking supermassive black holes, while smaller ones could populate dark matter halos, influencing the motion of stars and the formation of galactic structures. Detecting their effects would provide a concrete, observable counterpart to theoretical dark matter models, turning abstract physics into something measurable. Boson stars also offer solutions to puzzles that conventional dark matter models struggle with. For example, ultralight bosons can form coherent, stable structures rather than remaining diffuse. This could naturally account for some of the clumpy or core-like distributions of dark matter observed in dwarf galaxies, which sometimes conflict with predictions from cold dark matter simulations. By linking dark matter particles to macroscopic boson star structures, researchers may resolve long-standing tensions between theory and observation. Another reason boson stars matter is that they push the boundaries of fundamental physics. They exist at the intersection of quantum mechanics, general relativity, and cosmology. Ordinary stars can be understood mostly through classical physics and nuclear processes, but boson stars require quantum fields to describe their internal structure and general relativity to describe their gravitational behavior. Studying them could therefore illuminate how these two foundational pillars of physics, often difficult to reconcile, coexist in extreme environments. Finally, boson stars have the potential to expand our understanding of cosmic evolution. If they formed in the early universe, they could have influenced galaxy formation, seeded supermassive objects in galactic centers, and contributed to the overall structure of the cosmos. Detecting them would offer a new window into the universe's infancy, revealing processes that ordinary astrophysics cannot explain. In short, boson stars matter because they are more than theoretical curiosities. They may provide the first tangible link between observable astrophysical phenomena and the elusive particles that make up dark matter. By studying them, scientists could finally illuminate one of the darkest corners of cosmology, potentially solving a mystery that has persisted for nearly a century. They are objects that, though invisible, could shine a light on the deepest questions about the universe itself. One of the most fascinating aspects of boson stars is that they occupy a unique intersection between quantum mechanics and general relativity, two pillars of modern physics that are notoriously difficult to reconcile. On the one hand, general relativity describes the large-scale behavior of space-time, gravity, and massive objects like stars, black holes, and galaxies. On the other hand, quantum mechanics governs the microscopic world of particles, wave functions, and probabilistic interactions. Boson stars are remarkable because they require both frameworks to be fully understood, making them a rare and invaluable testing ground for fundamental physics. At the heart of a boson star lies a scalar field, a quantum field that permeates space and describes the distribution of bosons. These fields obey the principles of quantum field theory, meaning the particles within the star exist in collective quantum states and can overlap, oscillate, and interact according to quantum rules. The pressure preventing the star from collapsing is a quantum pressure, arising from the wave-like nature of bosons. This is fundamentally different from the classical pressure in ordinary stars, which comes from thermal energy, nuclear fusion, or degeneracy pressure of fermions. Yet, while quantum mechanics governs the internal structure of the boson star, gravity cannot be ignored. The mass of the star warps spacetime, and its self-gravitating nature is described by Einstein's equations of general relativity. The curvature of spacetime not only determines how the star holds itself together but also dictates how it interacts with surrounding matter, light, and even other boson stars. To model a boson star accurately, physicists must solve the coupled system of Einstein's equations and the quantum field equations for the scalar field. This is where the beauty, and the challenge, lies. Boson stars are literal embodiments of the interplay between the quantum and the cosmological. Because they exist at this interface, boson stars offer a laboratory for exploring the quantum aspects of gravity, a frontier that remains largely theoretical. Unlike black holes, where the event horizon hides most quantum details, boson stars are extended objects with observable effects that depend on quantum field behavior. By studying their stability, oscillations, mergers, and gravitational interactions, scientists can test predictions of scalar field theories and the way quantum mechanics manifests in curved spacetime. This is invaluable because experiments probing quantum gravity directly are currently beyond the reach of terrestrial laboratories. Boson stars bring the universe itself into the role of a cosmic experiment. Moreover, boson stars are directly linked to some of the most compelling ideas in modern physics, such as actions and other ultralight bosons, which are hypothesized in quantum field theories beyond the Standard Model. If these particles exist, they not only contribute to boson stars but could also explain dark matter. In this sense, boson stars act as a bridge between high-energy particle physics and astrophysics, allowing cosmic-scale observations to inform microscopic theories. Another fascinating consequence of this quantum relativistic interplay is the possibility of exotic phenomena. Because the bosons in a star exist in coherent quantum states, boson stars could exhibit behaviors that have no classical analog. For example, they might oscillate collectively, interfere with nearby scalar fields, or form stable configurations that persist across cosmic timescales in ways that classical stars never could. All of this is governed by a combination of quantum rules for the particles and relativistic rules for spacetime, illustrating how the two realms coexist in a single astrophysical object. Ultimately, boson stars are more than just exotic astrophysical entities. They are a natural laboratory where the deepest theories of physics converge. They demonstrate that quantum mechanics is not limited to subatomic particles, and general relativity is not limited to classical masses. Both are needed to understand the same object. Observing boson stars, or even indirectly detecting them through gravitational lensing, stellar motions, or gravitational waves, could provide critical insights into how the universe reconciles these two frameworks. In a sense, every boson star in the cosmos is a cosmic experiment in quantum gravity, silently testing the fundamental principles that underpin reality. While the theoretical framework for boson stars is robust and fascinating, it's crucial to emphasize the limits of observation. As of now, no boson star has been directly Confirmed. All discussions about their properties, behavior, and astrophysical significance remain firmly in the realm of theoretical physics and simulation-based prediction. Despite their compelling connection to dark matter and exotic quantum fields, they are hypothetical constructs, invisible, transparent, and elusive, making their detection extremely challenging. One of the primary observational challenges stems from their lack of electromagnetic emission. Unlike ordinary stars, which announce themselves with bright light across multiple wavelengths, boson stars produce no light at all. They do not undergo fusion, have no surface, and interact minimally with normal matter. This means that traditional astronomical methods, optical telescopes, radio dishes, X-ray observatories, and infrared imaging, are largely blind to their presence. Even in the heart of a galaxy, a boson star could be hiding entirely in plain sight, with no visible signature. Another limitation arises from their transparency and gravitational subtlety. While their gravity affects nearby stars, gas clouds, and light via lensing, the magnitude of these effects depends heavily on the mass and compactness of the boson star. Small or low-mass boson stars produce effects that are tiny, often lost in the background noise of stellar motions or interstellar matter. Even larger boson stars, while more detectable, can be easily mistaken for other massive compact objects, such as black holes or dense star clusters, because their gravitational influence can mimic these familiar astrophysical entities. Moreover, while gravitational wave detectors like LIGO and Virgo offer a promising avenue for indirect detection, the challenge lies in identifying signals that are unique to boson stars. Many predicted merger signals of boson stars could superficially resemble those of black holes or neutron stars. Disentangling these signals requires precise theoretical templates, advanced data analysis, and often, repeated observations to confirm that a particular waveform indeed originates from boson star physics rather than conventional astrophysical objects. Currently, this is a frontier in gravitational wave astronomy. Researchers are still developing and refining the models needed to confidently recognize boson star signatures. Even in the case of stellar motion studies, the challenge is significant. Subtle perturbations in stellar orbits, velocity dispersions, or the dynamics of galactic cores can hint at the presence of an unseen massive object, but they cannot unambiguously identify it as a boson star. Alternative explanations, such as compact clusters of ordinary dark matter, black holes, or other exotic astrophysical objects, must always be considered. This ambiguity is one of the reasons why no boson star can currently be claimed as observed. In addition, the parameter space for boson stars is vast. Their properties, mass, size, boson type, self-interaction strength, vary widely depending on the underlying particle physics. This diversity means that some boson stars could be extremely compact and massive, while others might be diffuse and almost indistinguishable from empty space. Detecting one subset does not guarantee we can detect them all, making the search inherently complex. Finally, it is important to highlight that boson stars are on the cutting edge of theoretical astrophysics. Their existence is consistent with quantum field theory and general relativity, but until we detect a signal uniquely attributable to a boson star, they remain a speculative but plausible solution to several outstanding problems, such as dark matter. They are an example of how theory often races ahead of observation, pushing astronomers and physicists to develop new methods and instruments capable of probing previously invisible realms of the universe. In short, while boson stars could be influencing the cosmos in profound ways, our current observational capabilities have not yet confirmed a single object. Detecting them will require a combination of gravitational wave astronomy, high-precision stellar surveys, careful analysis of gravitational lensing, and, most importantly, the development of theoretical models capable of producing distinct, testable predictions. Until then, boson stars remain one of the universe's most intriguing possibilities, an invisible population that may be silently shaping galaxies and dark matter halos alike. The study of boson stars is very much science in progress, a frontier of astrophysics and theoretical physics that is rapidly evolving but still full of unanswered questions. Unlike more familiar stellar objects, whose structure and behavior have been well characterized through centuries of observation, boson stars exist largely in the realm of hypothesis and mathematical modeling. Researchers are actively exploring their properties, their potential astrophysical signatures, and their implications for dark matter, but many aspects remain speculative. One reason this field is so dynamic is that boson stars sit at the intersection of multiple areas of physics. They require knowledge of quantum field theory to describe the bosons and their wave-like interactions. They require general relativity to describe the gravitational effects of the star as a whole. They also connect to cosmology, particle physics, and astrophysics, since their potential existence could explain dark matter distributions, influence galaxy formation, or even mimic supermassive black holes in galactic cores. Because of this interdisciplinary nature, progress requires collaboration across traditionally separate scientific domains, combining expertise in theory, computation, and observation. Despite decades of theoretical work, there are many open questions. For instance, what is the exact range of masses and sizes that boson stars can occupy in realistic cosmological scenarios? How do their internal quantum states evolve over time, especially under perturbations or during mergers? What role do self-interactions among bosons play in their formation, stability, and evolution? And critically, how can we distinguish boson stars observationally from black holes, neutron stars, or other exotic compact objects? Each of these questions represents an active area of research. On the observational front, scientists are pushing the limits of current instruments while preparing for next-generation facilities. Gravitational wave observatories, like LIGO, Virgo, Kagra, and the upcoming LISA mission, are central to this effort. They could detect mergers or oscillations unique to boson stars, but only if theoretical templates and signal processing methods are sufficiently developed. Similarly, precise astrometric surveys, such as Gaia, may reveal subtle gravitational perturbations on nearby stars, offering indirect clues about invisible objects in galactic halos. Even gravitational lensing studies are being leveraged to look for microlensing events that could betray the presence of compact, non-luminous objects consistent with boson stars. Another reason the field is cutting edge is that it intersects with fundamental particle physics, particularly with candidates for dark matter-like actions or other ultralight bosons. The detection of a boson star would not just confirm a new type of stellar object, it would provide strong evidence for the existence of these hypothesized particles, effectively linking observations on cosmic scales to particle physics experiments on Earth. Conversely, advances in particle physics could constrain the properties of bosons, which in turn refines the theoretical models of boson stars. This feedback loop makes the study of boson stars highly dynamic and full of potential breakthroughs. Because the field is still developing, many ideas remain speculative and under debate. The exact formation mechanisms of boson stars in the early universe are not fully understood. The population statistics, how many boson stars might exist, their distribution in galaxies, and their contribution to dark matter halos, are still largely unknown. Even basic questions about their maximum mass, potential to merge, and interaction with other compact objects require extensive numerical simulations and sophisticated theoretical modeling. In summary, boson stars are at the frontiers of modern science, representing a rare opportunity to explore phenomena where theory is ahead of observation. Scientists are actively developing models, refining simulations, and designing observational strategies to detect these invisible, exotic objects. The field is defined by open questions, ongoing debates, and the promise of discovery, making it one of the most exciting and intellectually rich areas of contemporary astrophysics. Studying boson stars is more than a theoretical exercise. It's a way to push the boundaries of what we know about the universe, from quantum particles to cosmic structures, and potentially to solve one of the greatest mysteries of all, the nature of dark matter. Let's return to the striking idea that began this journey. Not all stars need atoms. While most of the stars we are familiar with, our Sun, Sirius, or Betelgeuse, are made of atoms, with protons, neutrons, and electrons fusing to release light and heat, boson stars challenge this very notion. These exotic objects remind us that the universe can organize itself in ways that are fundamentally different from the patterns we see in ordinary matter. Instead of being composed of atomic nuclei and electrons, boson stars could be constructed entirely from fundamental quantum fields, with their properties governed by the wave-like nature of bosons rather than chemical reactions or nuclear fusion. In a boson star, the constituents are ultralight bosons, particles that obey the rules of quantum mechanics in a collective, coherent manner. Unlike atoms, which resist being in the same state due to the Pauli exclusion principle, bosons can occupy the same quantum state, allowing them to form these large, stable, gravitationally bound structures. The star itself is not glowing, not burning, and not composed of the familiar matter that populates the periodic table. Its stability arises from quantum pressure and gravitational equilibrium, not nuclear fusion. This reframing of what a star can be opens up a new vista in astrophysics. It forces us to think beyond the familiar categories of matter and radiation and consider the cosmos as a laboratory for exotic quantum objects. The laws of physics allow for structures that are completely dark, nearly invisible, yet massive enough to shape galaxies, bend light, and influence the orbits of stars. In essence, boson stars represent a new class of celestial objects where the fabric of space-time and the behavior of fundamental fields come together to produce something that mimics the gravitational effects of ordinary stars, yet is entirely alien in composition. By revisiting this hook, we are reminded that our understanding of the universe is still limited by what we can see and measure directly. Ordinary stars have guided much of astrophysics for centuries because their light illuminates the cosmos, but boson stars, invisible, silent, yet gravitationally potent, hint at a hidden population of cosmic objects that could be far more common than we imagine. Their existence would dramatically broaden our definition of a star, showing that a luminous fusion reactor is not the only way. The universe can assemble matter into a self-gravitating structure. The idea that stars can form from fundamental quantum fields rather than atoms also emphasizes the unity of physics at vastly different scales. Boson stars bring together concepts from particle physics, general relativity, and cosmology into a single, coherent object. They remind us that the universe is capable of surprises, that the rules governing the tiniest particles can manifest on astronomical scales, producing stars that defy our conventional expectations. In restating this hook, it becomes clear that boson stars are more than a theoretical curiosity. They challenge the very paradigm of what a star is. They open the door to entirely new ways of thinking about mass, gravity, and the composition of the cosmos. If boson stars exist, the universe is not merely a collection of atoms and light, but a more intricate tapestry in which quantum fields themselves can sculpt the heavens. And now, we arrive at the final awe-inspiring thought. If boson stars exist, the universe is stranger than we ever imagined. After journeying through the realms of theory, quantum fields, and gravitational physics, it becomes clear that the cosmos may be far more exotic than what meets the eye. We are accustomed to stars that shine, planets that orbit, and galaxies that glow with the light of billions of stars. Yet, lurking invisibly among them could be entire populations of stars that emit no light, have no hard surface, and are built not from atoms but from the enigmatic fabric of quantum fields. The idea itself is almost poetic. Imagine an object as massive as a star, exerting the same gravitational influence, perhaps sitting in the heart of a galaxy, bending light and shaping the orbits of nearby stars, yet utterly invisible. Unlike a black hole, it may have no singularity and no event horizon. Unlike ordinary stars, it does not shine or fuse atoms. Its very existence is a testament to the subtle, often counterintuitive rules of quantum mechanics married with the inexorable pull of gravity. Such objects are not merely theoretical. They are potential witnesses to the deep structure of the universe, signaling that the cosmos is not only stranger than we see but stranger than we have ever dared to imagine. Boson stars also invite us to reflect on our methods of exploration. For centuries, our understanding of the universe has been dominated by what we can detect with light, optical, radio, X-ray, and gamma-ray emissions. But boson stars challenge this paradigm, reminding us that the universe communicates in more ways than photons alone. Gravity, the silent architect of cosmic structures, may be the messenger for these hidden stars. Through the subtle motions of visible stars, gravitational lensing, or the faint whispers of gravitational waves, we may one day see the invisible and finally confirm that such exotic stars are real. Furthermore, their existence would link the infinitesimal world of quantum fields with the grandeur of galaxies, connecting the microcosm and the macrocosm in ways that defy conventional intuition. The very particles that are hypothesized to make up dark matter, ultralight bosons, could aggregate into massive, coherent structures that persist across billions of years, influencing the universe on scales far beyond what we normally associate with quantum mechanics. This is a profound reminder that the cosmos operates on levels of complexity and subtlety that challenge human imagination. The wonder of boson stars also lies in the open-ended nature of the field. No one knows for certain how many may exist, how they are distributed, or how exactly they influence galaxies and dark matter. Each discovery, each gravitational wave, each anomaly in stellar motion could potentially reveal a hidden population of cosmic objects that have eluded detection until now. The universe is not a static or fully charted territory. It is alive with possibilities, with hidden structures and phenomena waiting to be unveiled by careful observation and creative theory. Finally, boson stars leave us with a humbling lesson. The universe is not limited to our conventional understanding of matter and energy. Stars, planets, and black holes are only part of the story. The cosmos may also host silent, invisible stars built entirely from the fundamental fields that pervade space, demonstrating that nature is both inventive and elusive. Contemplating boson stars encourages curiosity, and a recognition of the profound mysteries still awaiting discovery. So, as we step back and reflect, the takeaway is simple yet profound. If boson stars exist, the universe is far stranger, more complex, and more wondrous than we ever imagined. They challenge our definitions, expand our imagination, and promise a universe richer and more mysterious than any story we have yet told. In the quiet, invisible structures of the cosmos, the laws of quantum mechanics and general relativity conspire to create objects that may, one day, redefine what it means to be a star. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.